Hey everyone, welcome back to Aram DevHub. I'm Darshan. Today we're building something really exciting. An AI-powered code auditor, written entirely in Rust. Now here's what makes this special. This isn't just some basic script that runs a few checks. No, this is a full-blown AI agent. It can think, it can explore, and it makes decisions on its own. You point it at any GitHub repository, and it goes to work. It clones the code, explores the file structure, reads through source files, searches for patterns, and then reports every bug and security issue it finds. Just like how Claude or GPT uses tools to work with code, that's exactly what we're building here. So what will you walk away with today? First, a production-ready CLI tool, one that can analyze any GitHub repository you throw at it. Second, you'll understand agentic architecture, where the LLM actually calls tools like list files, read file, and search code. Third, we've got two analysis modes. Tool calling mode for smart exploration, and single call mode when you need speed. Fourth, a comprehensive Markdown report generator, because what good is finding bugs if you can't report them properly? And fifth, code you can actually extend, add your own custom tools, make it your own. We are talking about 2,500 lines of production Rust code, spread across 14 different files. This is the real deal. Now before we jump in, a quick note. I've already built this complete project. The full source code is on GitHub. Links in the description. What I'm going to do is walk you through everything. The architecture, the design patterns, how each piece connects to the others. Think of this as a guided tour through production Rust AI code. You'll learn the why behind every decision I made. Before we dive in, if you're into Rust and AI, hit that subscribe button, ring the notification bell. I drop new content every week. Join our Discord community too. Links in the description. Great place to share projects and get help. And if this tutorial helps you build something awesome, consider buying me a coffee. Every bit helps fund more tutorials like this. Alright, let's build this code auditor. Before we write any code, let's understand what we're building. The mental model is everything. Our code auditor has four main pillars. I like to think of them as body parts of our AI agent. First, the body. That's our CLI, built with the CLAP library. It handles all the argument parsing, validation, and user interaction. Second, the brain. That's the agent module. This is where the magic happens. It connects to Ollama, manages conversation history, and decides which tools to call next. Third, the hands. Those are the tools. 6 different tools the AI can use to interact with codebases, list files, read files, search code, and more. Fourth, the memory. That's our configuration and models, data structures for issues, reports, and settings, the glue that ties everything together. Let me walk you through the agentic loop. This is the core innovation of our system. Step 1. The agent receives a task, something like, analyze this repository for bugs and security issues. Step 2. The LLM reads the tool definitions we give it, and it decides what to do first. Usually it calls list files on the root directory. Step 3. Our Rust code executes that tool call, and returns the results back to the LLM. Step 4. The LLM processes those results, and decides what to do next. Maybe it sees an interesting source file and calls read file. Step 5. This loop continues. The LLM calls tools. We execute them. It processes results, over and over, until it decides it's done and calls finish analysis. Step 6. We collect all the issues it found and generate a beautiful Markdown report. This is exactly how Claude and GPT work with tools behind the scenes. We're building that same capability. Let me walk you through our project structure. This is a real production layout. At the root level, we have cargo.toml with 15 dependencies, a configuration file called .codeauditor.toml, and our README. Then, inside the source folder, here's where it gets interesting. We have 4 core files at the root. Main.rs is our entry point. About 270 lines handling the workflow. CLI.rs handles argument parsing. 350 lines with comprehensive options. Config.s manages all our settings. 390 lines with 4 configuration structs, and models.s contains our data structures for issues, reports, and files. Then we have subdirectories. Each one is a Rust module. The agent folder. That's where agent.agw lives, 560 lines implementing both analysis modes, and tools.rsins, 540 lines defining all 6 tools. The repo folder has cloner.rsins, handles Git repository cloning. The analysis folder has aggregator.rsins. For collecting and organizing issues, the report folder has generator.rs, creates our Markdown output, plus each folder has a mod.rs file to tie things together. 14 Rust files total. About 2,500 lines of production code. A fully functional AI agent. Here's an important design decision you should understand. We have 2 analysis modes. Tool calling mode. This is the true agentic approach. The LLM explores autonomously. It calls list files, read file, search code, all on its own. It's smart. It focuses on important files, searches for specific patterns, makes decisions based on what it finds, but it needs multiple API calls, single call mode. This is the speed approach. We read all source files at once, concatenate them into one big prompt, and send everything in a single API call. It's fast, efficient, great for cloud models with rate limits, but less intelligent because the LLM sees everything at once. In our config, you just set single uscl calibers mode to true for speed, or false for the full agentic experience. This flexibility is crucial for different use cases. Every Rust project starts with cargo.toml. Let's break down our dependencies. Each one is carefully chosen for production use. We start with the package section. Name is Code Auditor, version 0.1.0, edition 2021. We set keywords like code review, audit, LM, and Ollama. These matter if you publish to crates.io. For CLI parsing we use CLAT version 4, with the derive and end features. The derive feature gives us macros. Just annotate a struct and CLAT generates the parser for you. The end feature lets us read from environment variables as fallbacks. For async, we use Tokio with full features. AI agents are inherently async. We wait for LLM responses. Wait for Git clones. Wait for file reads. Tokio handles all this efficiently without blocking. For repository cloning, we use Git2, that's Rust bindings for libgit2. It handles authentication, progress tracking, shallow clones, everything we need for professional Git operations. For HTTP requests to Ollama, we use aiagent with the JSON feature, built on HyperWest with the JSON feature, built on HyperWec, handles connection pooling, HTTPS, timeouts, all the production essentials. For serialization, we have srd and srd JSON, .json, LLMs speak text, tools speak JSON, reports need structured data. srd bridges all of this seamlessly. We also use the tom crate. For parsing our configuration file, toml is human-friendly, way easier to read than JSON. For logging, we use tracing and tracing subscriber. Stop using println for debugging, seriously. Tracing gives you structured logging. Async aware, timestamps, log levels, module filtering. It's the professional way. For errors, we use anyhow and thiserror. Anyhow is for application errors, great for main functions. Gives you helpful context. Thiserror is for library errors. Custom types with proper messages. Together, they give you flexibility and type safety. A few more essentials. Chrono for timestamps in our reports, Indicati for beautiful progress bars during Git clone, walkdir for recursive file system traversal, tempfile for temporary directories when cloning, futures for async utilities. That's our foundation. 15 carefully chosen dependencies for a production AI agent. Let's talk about config.rs. This file is about 380 lines. Here's the thing, hard coding settings is a rookie mistake. Professional tools are configurable. You shouldn't need to recompile just to change a setting. We have a root config struct with 4 sections. General config handles output settings and concurrency. Model config handles LLM settings, model name, Ollama URL, temperature, timeout, and that single unsid call, not qual asyncrust flag. Scanner config handles file discovery, maximum files, extensions, exclude patterns. Report config handles output formatting, snippets, summaries, grouping. This is all Serde powered. We derive, serialize and deserialize. And the TEML parcel handles everything automatically. General config has 3 fields. Output is the default report file name. We use code of02 audit of02 report.mt. Verbose controls logging verbosity. Concurrency sets how many files to analyze in parallel. We implement the default trait to provide. So if there's no config file, the tool still works out of the box. Model. This is all behavior. Name is the Ollama model. Default is Llama 3.2 latest. Ollama URL is the API endpoint. Default is localhost port 114.34. Temperature controls creativity. We use 0.1 for focused, deterministic analysis. Max tokens can limit response length. Timeout seconds prevents hanging. Default is 300 seconds. Retries for fault tolerance. Default is 3 attempts. And single call mode. The Boolean that switches between our 2 analysis approaches. Scanner max caps the number of files. Default 100. Too many files overwhelm the LLM. Max chunk lines limits lines per chunk. Default 4000. Extensions is a list of file types to analyze. Rust, Python, JavaScript, TypeScript, Go, Java, C and more. Excludes is patterns to skip. .git folder, target folder, node modules, vendor directories. This prevents us from analyzing generated code and dependencies. The load function reads from a path and parses toml. Load unsession default looks for code auditor.toml in the current directory. Load unsession from repository for a config file checks the cloned repository for a config file. This layered approach means use repo config if present, else use local config, else use defaults, flexible and user-friendly. The merge use iritaus. Pitrovog's function is clever. CLI arguments override config file settings. If you specify model on the command line, it beats the config file value. We check if each argument differs from its default before overriding. This lets users set some options in config and others on the command line. Before starting analysis, we validate everything. Temperature must be between 0 and 2. Max files must be positive. Model name can't be empty. This is fail-fast design. Clear errors at startup are way better than weird behavior later. We use anyhow's bail macro for this. It creates an error and returns early. Perfect for validation logic. Now let's look at CLI.rs, about 350 lines of code. The CLI is how users interact with our tool. Built with claps derive macros. It provides a professional command line experience. We define args with the derive parser macro. It has many fields for a full-featured CLI. Repo is the GitHub URL. Required and positional. With a short R flag, model optionally overrides the config. Output sets the report path. Fornet lets you choose between Markdown and JSON output. Branch specifies which branch to clone. Local lets you analyze a directory instead of cloning. Then we have scanning options. Max files, max chunk lines. Extensions as a list. Exclude patterns. And verbosity flags, verbose for debug logging. Quiet for minimal output. Clap generates all help text, version info, and error messages automatically. We define output format as an enum, with Markdown and JSON variants. The clap value enum derive makes it a valid CLI argument. Users can specify format Markdown or format JSON. Default is Markdown. Most users want a readable report. The parse_warg function is simple. Just claps parser. The derive macro does the heavy lifting. The validate function is more thorough. It checks that the repo URL looks valid. Must start with HTTP or DL looks valid. Must start with HTTP or DAT. It validates the Ollama URL format. It catches conflicting options. You can't specify conflicting repo settings. Temperature must be in valid range. Early validation prevents confusing errors down the road. The log level function returns appropriate tracing levels based on flags. If quiet, return warn. Only warnings and errors shown. If verbose, return debug. Maximum detail for debugging. Otherwise, info. Normal operation. This gives users control without overwhelming them with defaults. The effective extensions method returns CLI extensions if provided. Otherwise uses our default list. The effective extern excludes method is smarter. It adds to defaults rather than replacing them. Users can specify additional excludes, and we combine them with standard ones like .git and node.snaftia-waj. This is user-friendly design. You don't lose important defaults when customizing. Every module has tests. We test that default extensions contain common languages. We test that invalid URLs fail validation. We test that conflicting options get caught. We test that log levels are selected correctly. Run cargo tests to verify everything works. Tests are your safety net. Now we're getting to the exciting part. Let's look at tools.rs in the agent folder. About 540 lines. These are the tools that give our AI agent hands. This is what transforms a chatbot into an autonomous agent. We define tool definition with two fields, tool type, always function for Ollama, and function, that's a function definition struct. Function definition struct. Function definition has name, description, and parameters as a JSON schema. The AI reads this schema to understand what arguments each tool accepts. Good descriptions lead to good tool use. Let me walk through our 6 tools. Tool 1, list files, takes a directory path, returns all file names in that directory. This lets the AI explore the codebase structure. Tool 2, read file, takes a file path, returns the file contents. The AI reads source code to analyze it. Tool 3, search code, takes a pattern, finds matching lines across the entire codebase, like grep, but the AI decides what to search for. Tool 4, get file info, takes a path, returns metadata. Language, line count, file size, quick info without reading the whole file. Tool 5, report issue. Takes structured data, file path, line number, severity, category, title, description, and a suggestion for fixing it. This is how the AI logs problems it finds. Tool 6, finish analysis, takes no arguments. The AI calls this when it's done exploring. Our signal to stop the loop. The tool executor struct holds 2 things, the repo root path, so we know where to look for files, and a vector of reported issues. Every time the AI calls report issue, we add to this list. It's created once per analysis, and called multiple times during the agent loop. The execute method takes a tool call and returns a tool result. It matches on the tool name and calls the right handler. Let's look at list files in detail. We read a directory and return its entries. First, security checks. The path must be inside the repo root. We don't allow directory traversal attacks. We skip hidden files that start with dots. Skip node known. Skip target directories. We mark directories with a trailing slash, so the AI can tell files from folders. Simple, minimal output. Just what the AI needs to make decisions. Read file is the workhorse of our tools. We validate the path exists. We verify it's inside the repo. Security first. We check file size, limit to 100 KB. We don't want to overwhelm the LLM context. Then we read and return the raw content. No line numbers, no formatting, minimal tokens for maximum efficiency. The AI doesn't need pretty printing, it needs data. Search code is powerful. It takes a pattern and an optional max results limit. We recursively walk the directory tree with walkdir. For each source file matching our extensions, Rust, Python, JavaScript, and so on. We check each line for the pattern. Matches include the file path and line number. This lets the AI find specific patterns across the entire codebase. Find all uses of unwrap. Or, search for Todo comments. Get file info returns compact metadata. We get the file's metadata from the file system, count the lines, detect the language from the extension. The output is minimal, like Rust 150 lines, 4096 bytes, formatted as 3, separated values. Maximum information, minimum tokens. That's our goal. This is how the AI logs its findings. It sends structured JSON, file path, line number, severity level, category, title, description, and a suggestion. We create a reported issue struct, push it to our vector return just, OK, 2 characters. The AI doesn't need verbose confirmations. These issues get collected and become our final report. Let me highlight our token optimization strategy. This is crucial for cost and speed. Old approach. Return formatted, verbose responses. Like successfully listed 12 files in directory src. New approach. Return minimal data. Just, zerk, and the file names. For read file, we removed line number prefixes. That was adding 7 characters per line. For a 500-line file, that's 3,500 extra characters. About 1,000 wasted tokens. Every tool returns just the essential data. The AI is smart enough to understand raw output. This optimization cuts token usage by 15 to 50% depending on the tool. The getToolDefinitions function returns all 6 tools as tool definition structs. This is what we send to Ollama's API. Each definition includes a clear description. The AI reads these to understand its capabilities. It includes a JSON schema for parameters, types, descriptions, required fields. Good descriptions lead to good tool use. Spend time on these. Let me step back for a moment. This architecture has beautiful properties. The tools know nothing about the agent. The agent knows nothing about tool internals. They communicate through a clean interface. Tool call and tool result types. This means you can swap implementations. Want caching? Wrap the executor. Want logging? Add a decorator. Want new tools? Just add another match arm. Trait-based design in Rust AML. Trait-based design in Rust enables this composition. It's extensible without inheritance hierarchies. Now we reach agent.rs, about 560 lines. This is the brain of our system. This is where reasoning happens, where tools get called, where the AI makes decisions. Agent config holds our runtime settings, Ollama URL and model name, temperature for controlling creativity, max iterations, default 50, prevents infinite loops, timeout in seconds, single call mode Boolean, and max context messages for the sliding window. The sliding window is important. It limits how many tool results stay in context. Old messages get pruned. This prevents context overflow during long sessions. The codeanalysis struct holds 5 things: config, our runtime settings, an HTTP client for talking to Ollama, a tool executor for running tools, a messages vector for conversation history, and the repo root path. The constructor creates everything. The HTTP client gets a timeout from config. The tool executor gets the repo path. Run analysis is our entry point. Very simple. It checks single call mode and dispatches to the right method. If true, call run single call analysis. The fast path. If false, call run tool calling analysis. The agentic path. Simple dispatch. Complex behavior hidden behind clean interfaces. Let's walk through single call mode first. The collect source files function walks the repository. Reads all source files into a hash map. We filter by extensions, skip hidden files, skip common excludes, limit to 100 kilobs per file. Then we build a prompt. It starts with instructions: analyze these files, report issues as JSON, 1 per line. Then we concatenate all file contents, with clear markers, file headers and code blocks. We send this to Ollama in one API call. Fast. Efficient. No looping. Finally, parse under issues other SEPA from _response extracts JSON objects from the LLM output. Each line starting with an opening brace gets parsed as an issue. Now let's walk through tool calling mode. This is where the real magic happens. We start with a system prompt, defining the AI's role. You are an expert code reviewer. You have tools to explore the code base. Use them to find issues. We add an initial user message: analyze this repository. Start by exploring the file structure. Then the loop begins, up to max iterations times. We call chat usqueeth times quote, get an LLM response. If the response includes tool calls, we execute each one. If the tool is finished under analysis, we break. Analysis complete. For other tools, we execute via the tool executor. Add the result to messages. Call prune alt-jas messages to keep context manageable. If there are no tool calls, the LLM sent text. We check if it says complete or finished. That's a natural language completion signal. Otherwise, we prompt it to continue. After the loop, we collect issues from the tool executor and return them. The system prompt is critical. Let me share the key parts. You are an expert code reviewer and security auditor. Your task is to analyze a code repository for issues. We list available tools with descriptions. List stuffed files for exploration, read file for contents, search code for patterns, get file info for metadata, report issue for findings. Finish analysis when done. We describe the process. Start by listing files in root, identify source files. Read and analyze each one, report issues. When finished, call finish analysis. We specify what to look for: bugs, security issues, performance problems, code quality concerns. Good prompt engineering is half the battle. This prompt prevents loops, ensures structured exploration, produces consistent results. The prune our old us messages method is clever. As the agent works, conversation history grows. Tool results, especially file contents, add thousands of tokens. We keep the system prompt. That's message 0. We keep the initial user message, message 1. Then we keep only the last end tool messages, configured by max.context-messages, default 10. Older messages get removed. This prevents context overflow, keeps Cloud API costs down, avoids errors from exceeding limits. The chat with tools method handles Ollama communication. We build the request, model name, messages vector, tool definitions as JSON, stream false, temperature option, repost to Ollama's chat endpoint, handle errors, timeouts, connection failures, API errors, parse the response, add the assistant message to history, return. If there are tool calls, the loop continues. Notice the error handling throughout. We use map error to add context, like request timed out after 300 seconds, try a different model. Specific errors get specific suggestions. Connection refused. Is Ollama running? Model not found? Try pulling the model first. This layered approach, specific at bottom, general at top, produces helpful user-facing messages. Let's look at models.rs. This defines all our core data structures. Severity has 4 levels: low, medium, high, critical. We implement display for human-readable output. Just the lowercase name. The emoji method returns visual indicators: green circle for low, yellow for medium, orange for high, red circle for critical. These appear in reports for quick scanning. Category classifies issues: bug, security, performance, style, documentation, best practice, or other with a custom string. We implement from trait for string conversion. Security becomes security. Unknown strings become other with the original text preserved. Issue is our core finding type. Fields include file, $\sock/time. Optional and $sock, line for ranges, severity, category, title, description, suggestion for how to fix, and optional code snippet. The line word range method formats nicely. 42 for a single line. 42 for Avida, for ranges. Analyzed file groups issues by file, with metadata, path, language, line count, success status. Issue summary counts issues by severity, totals for critical, high, medium, and low. Report metadata captures analysis context, repo URL, date, model used, files analyzed, duration. Report combines everything, metadata, project overview, analyzed files, summary, recommendations. Now let's look at the repo folder, specifically cloner.rs, about 270 lines. This handles Git repository cloning using the Git2 library. Clone result represents a successful clone. It holds the repository from Git2, the path to the cloned repo, and an optional tempdir handle. The tempdir keeps the temporary directory alive. When it gets dropped, the directory is cleaned up. Repo path returns a reference to the path. Into path consumes the result and returns the path. If there's a temp directory, we keep it around using the keep method. Clone options configures how we clone. Branch. Which branch to check out? None means default branch. Depth. For shallow clones, we default to 1 for speed, show progress, whether to show a progress bar, target dir, where to clone to. None means use a temp directory. The clone _ repository function is the main entry point. We determine the target path. If a target directory is specified and exists, we try to open it as an existing repo. Otherwise, we create a temp directory. We set up a progress bar using indicative. Users like to see something happening during long operations. We configure remote callbacks for transfer progress. Update the progress bar as objects are received. Set up fetch options. Apply depth for shallow clones. Create a repo builder. Set the branch if specified. Clone the repository. Handle errors with helpful context. Return the clone result with repo, path, and tempdir. A few helper functions. Open uncertificate not a repository opens an existing local repo. For when users want to analyze a directory instead of cloning. Parse GitHub URL extracts owner and repo name from URLs. Handles both HTTPS and SSH formats. Get current branch and get current commit return metadata about the checked out state. Cleanup repository handles cleanup, though with tempdir it's mostly automatic. The analysis folder contains aggregator.rsers, about 290 lines. This handles issue aggregation and statistics. Aggregate_rs collects all issues from analyzed files into one vector. Sort issues by severity puts critical issues first. Then high, then medium, then low. Group by file returns a hash map. File path as key. Vector of issues as value. Group by severity groups by severity level instead. Group by category groups by issue category. Top issues returns the n most severe issues. Language distribution computes how many files of each language were analyzed. Issue density calculates issues per 1,000 lines of code, helps identify problematic files. Generates summary text creates a human-readable summary of statistics. Most problematic files identifies files with the most issues. Identify patterns finds common issue titles and categories. Helps spot recurring problems across the codebase. The module has comprehensive tests. Test aggregate issues verifies collection works correctly. Test sort issues by severity checks ordering. Test group by category validates grouping. Test top issues checks we get the right number. Test issue density verifies the calculation. Tests are your safety net. Don't skip them. The report folder contains generator.rs, about 480 lines. This generates our Markdown output. Generate Markdown report is the main function. Takes a report struct, returns a complete Markdown string. It calls several section generators. Metadata, table of contents, overview, summary, issues, recommendations, footer. Each section is built separately, then concatenated together. Generate metadata section creates the report header, repository URL, analysis date, model used, file count, duration. Generate table of contents creates navigation links. One entry per file with issues. Generate overview section displays the project description if available. Generate summary section shows issue counts and statistics. Critical, high, medium, low. Language distribution, most problematic files. Generate issues section iterates through analyzed files. Generate file issues section creates a section for each file. File path as header, then each issue. Generate issue block formats a single issue. Severity emoji. Title. Line number. Description, suggestion, code snippet if available. The formatting makes issues easy to scan. Emojis provide visual urgency indicators. Generate recommendations section lists suggestions for improvement. Generate footer adds a closing note. Tool name, generation timestamp, write report, writes Markdown to a file path. Generate JSON report serializes the report struct as JSON. Write JSON report, writes JSON to a file path. Users can choose their preferred format via the CLI. Finally, let's look at main.rs, about 270 lines. This is our entry point. The main function is simple. Parse arguments using clap. Initialize logging with tracing. Call run audit. That's where the real work happens. Handle any errors and exit appropriately. Init logging sets up tracing based on verbosity flags. Quiet mode shows only warnings and errors. Normal mode shows info level. Verbose mode shows debug level. This gives users control over output noise. Run audit orchestrates the entire process. First, load configuration. Check for config file. Merge with CLI arguments. Second, get the repository. Clone from URL or open local path. Third, create the agent with config settings and repo path. Fourth, run analysis, either single call or tool calling mode. Fifth, build the report. Metadata, files, issues, summary. Sixth, write output. Markdown or JSON based on format flag. Finally, return the output path. Load config tries several sources. If a config path is specified, use that. Otherwise, look for tom-code-auditor.toml in current directory. Otherwise, look for config in the cloned repo. Otherwise, use defaults. Then merge CLI arguments on top. This layered approach is flexible and user-friendly. Get repository handles both cases. If local is specified with a path, open that directory. Otherwise, clone from the URL. Set up clone from the URL. Depth, progress. Return the path to analyze. Alright, let's see it in action. I have Ollama running with qwen 2.5 coder 480b. Let me run the command. Cargo run, repo in a GitHub URL. Watch the output. First it owns the repository. Shows a progress bar. Then it initializes the agent, shows model name, URL, and mode. Notice we're using single call mode here. This is much faster, perfect for demos and when you want quick results. The agent reads all source files at once, concatenates them into one prompt, sends everything to the LLM in a single API call. You'll see it processing, analyzing the entire code base, looking for bugs, security issues, code quality problems. This takes maybe 30 to 60 seconds depending on repo size, way faster than the tool calling approach which can take several minutes. And done. Analysis complete. We get a summary. Files analyzed, total issues found, breakdown by severity. Critical, high, medium, low. Report saved to code audit report.mt. Let's open the report and see what it found. Let's open the report. Header section, date, model, files analyzed, duration, summary section. Critical issues, high, medium, low, visual at a glance, then file by file breakdown. Each issue has file path, line number, severity emoji, category, title, description, suggestion for fixing. This is a professional audit report, generated automatically by an AI agent that explored the code base on its own. Pretty amazing when you think about it. Let me summarize what we built. 14 source files, about 2,500 lines of production Rust code. 2 analysis modes. Tool calling for intelligence. Single call for speed. 6 tools giving the AI hands to interact with code. Comprehensive configuration. TOML files, CLI overrides, validation, token optimization, reducing usage up to 50%, sliding window context management, preventing overflow, professional report generation, Markdown in JSON. This isn't a toy. This is a real tool you can use and extend. Here are ideas to take this further. Add a regex grep tool for more powerful searching. Implement caching to avoid rereading files. Add support for more LLM providers. OpenAI, Anthropic, Gemini. Create custom issue categories for your domain. Build a web UI with Axum or Actix. Add GitHub Actions integration for automated audits. The architecture supports all of this. You got the foundation. Time for action. Drop a comment. What tool are you adding first? What repeals will you audit? Subscribe for more Rust and AI content. Multi-agent systems coming next. Join the Discord. Share your projects. Get help. Connect with the community. Star the GitHub repo if it's useful. And if this saved you time, buy me a coffee. Thanks for watching. I'm Darshan from Aram DevHub. Keep building, keep learning, and remember, AI agents in Rust are the future. Now go audit some code. Peace.